Thanks so much. Sorry for the long bio. I feel like I want to thank you all for being here. It was just my way of saying that, yes, I'm that French person that used to be a user on those French supercomputers that some of you have administered. And it's a real pleasure to be here for me today because it's my first Lustre user group. And now it's our turn to show you what we try to do. And I want to give a couple of minutes for Prethvi to introduce themselves to you. So Prethvi, please introduce yourself.
Sure. My name is Prethvi Kashinkunti. I'm also part of Julie's data center systems engineering group. And on Selene, I've been helping to support our Lustre file system and bring it into production for our users.
Thank you. So today, we're going to try to use a different vision than the classical HPC one. We're going to try to show you the challenge of AI at scale and why we designed Selene like that. We're going to spend some time showing what's specific about the DGXA100 and Selene and why some Lustre features were very critical to us. We're going to discuss the storage architecture in details. And we'll spend some time at the end showing you some synthetic and real application performance driven by what we do in benchmark and the requests from users. And hopefully that's going to be interesting to you. And the last topic is a topic that is very dear to us and for which we got a lot of help from the community, which is client caching. How can that help us do deep learning on a daily basis? So first, I'm going to start with what is it that we look at in terms of workloads, and what do we call, our HPC workloads? What do we need for storage? And especially, I'm going to start with compute and showing you that the model is getting more complex. So this is a little go back into time, and that's the number of petaflops per day training for compute. And those, you see the different models. So if you guys follow the news, you've heard about BERT, about GPT and those things. And that's the evolution of it. And that's how fast it went. Because if you look into the left side, you see it's only 2012. And the scale is a logarithmic scale. What that means also is that the data sets that those models are being trained on are getting larger and larger and larger very fast. So storage that, historically the AI community didn't very much look into is becoming very important. Right now, a car coming back from, every 8 hours of driving is going to come back with 1 terabyte of data. So for people having a fleet, that gives you an idea of how much turnaround we're going to see. As I said, so I come from academia. I'm a chemist by training, and I joined NVIDIA around the left-hand side of that picture where, we were training things in 20 days on a single GPU. And as you see that slide goes from like one card, then one server, then a bigger server, then a small cluster, and then we're entering really large clusters. In particular, the one on the right that you can see here was made of DGX2, and it was the top 20 at a time in the top 500, and that was one of the biggest cluster we had to build. So the irony for me was like after, working on those clusters and bugging people that they were not doing what I want, management said, okay, Julie, so how about you guys build one? And so we started building one, and that was our first iteration. It was the DGX2 SuperPOD, and it was already pretty good. But then we figured we wanted to go one step further and see if we can be at a real scale. And this is Selene. So I really enjoy seeing the introduction for University of Florida because Hypergator is the first instance of a SuperPOD in the world, and it's really beautiful. So this is our internal instance. This is Selene, which is the top 5 right now on the top 500, and top 5 on Grid 500, and top 1 for a single scalable unit. So here, not only we build ourselves a cluster to experiment ourselves, but we had some very careful requirements of what we wanted to do. In particular, our first requirement was not to be in the top 500, etc. It was to be a super fast AI machine. And what that means is, instead of storage requirement, when we started that project, we started the design, people say, yeah, do you think you can do 1 terabyte per second reads and possibly write? I was like, ooh, okay. This is a scale we haven't looked into yet, but let's have a look at it. So Selene is made of 560 servers, but since each server has 8 GPUs, it's more than 4K GPUs. And basically, we need to feed those GPUs. The reason is not only we needed a computer for benchmarks, etc., but at NVIDIA, we use our clusters very heavily. So our biggest demanding source of users are our colleagues. So it's very challenging because the requirements for operational level in terms of performance are very high. The clusters are used for a wide range of applications that are usually not as advertised then we want to admit it, but we do full continuous integration. For example, every night we make sure that workload at scale haven't had a perf regression. At NVIDIA, if you want to push a merge request into the top of tree of some DL codes, you can't do it until it passed performance at scale. We also have a strong community of researchers, and we also have commercial applications like automotive or QA. And basically, we designed Selene to be able to cater to all those users. So what is Selene made of? Selene is made of DGXA100. The DGXA100 is a very interesting server. In particular, so you see here we have those 8 GPUs, but we were one of the first supercomputers with a dual AMD Rome CPU, the 7742, and we have 8 compute NICs and 2 storage NICs. So you can see here the back of the machine, and you can imagine what the cabling is going to look like. We're going to show you to you a little bit afterwards. But what that means for us in relation to what Peter presented yesterday and what also presented is we're going to be heavily multi-rail. Multi-rail for us was needed from day one. The other thing is using AMD ROMs, we also needed very new Linux kernels, or at least Linux kernel that had the support for those CPUs day one. And we also cater to a community of AI folks and deep learning folks. So we are one of the largest supercomputer with an Ubuntu Linux OS. So we run Ubuntu in user space. And since day one, even when Ubuntu 2004 was not out, we've been aligning on a 5.4 kernel. So that means very early we look into HWE and very recent kernels for that reason. All of this, again, to reach performance. All of this to make sure that we could provide the best to everybody. And of course, that comes with a fun, interesting design constraints. So each machine is up to 6.5 kilowatts per machine, and as a 6U of height. So now we had a bunch of servers, and we had another constraint. We're a company, and since day one, we wanted to make sure everybody could get a SuperPOD, a smaller one, a bigger one, a piece of it. And basically, we designed with 1K pods, and we always designed to be extensible. And extensible and scale and performance don't always go together. So basically, we designed a modular IB factory where basically we needed to achieve that 1 terabyte per second for storage. So we needed to separate compute and storage. And that's what you can see here. And not only we're multi-rail, but for compute reasons and the fact that most of the deep learning algorithms rely heavily on or reduced ring entry based, we needed to be rail optimized. So we end up with a very interesting fabric design. And then we wanted to be able to extend them. So at the top level, we function, at least Selene is made of quads. Each quad is 1K GPU pod. And all those quads go together in a data center. Here's one quad here, one quad here, one quad here. This is a synthetic image, but in real life, the cluster really looks like that. So that means instead of design, we don't have a core, or we don't have somewhere where we have all our storage and all our fabric, everything has to be integrated so that we can extend. And in particular for storage, that will mean each quad is going to have its old set of Lustre and Pliant that we're going to have to extend as we go. So let's go a little bit more into Selene's storage architecture. So as I mentioned, we need to be able to extend and have any scale. So for example, here in the top, what you see is what we call scalable units. The way we do it is one can get a 10-node SuperPOD, a 20, a 40, an 80, etc. And for storage, we use a fabric that has a subscription ratio that depends on the scale one runs at. And this is how we're connected. So basically, each node has 2 rails, each going to a lift switch, right? And then it goes to the spine. And until this level, there's no need to be a core. But if you go higher, then you imagine we will need to have a core. And the storage sits here in the middle, and each storage bit happens as you extend the number of scalable units. So this is the easier drawing as you go at scale. This is what it looks like. So you can see the slide is much more engineering. Basically, why am I showing that? Is one additional aspect we had is our users being performance oriented. We can't have a fabric failure. We can't have a performance drop because we lost the cables, right? And overall in Selene, we have more than 60 kilometers of cable, something like 11,000 cables. So we have to be somewhat resilient to failure. And the way it's designed is to be resilient to switch failure at the spine core level so that we don't have more than 10% of perf hit to the peak bandwidth, right? So all of this was designed so that at any point in time, we could keep a level of operation that would involve performance for the storage. I'm going to give the mic to Prethvi, and he's going to describe to you what's inside the racks for storage.
Sure. Thanks, Julie. So yeah, like she mentioned, I'm going to talk a bit about our configuration and a little bit of how it ends up working in practice. So on this slide, we have a picture on the right, which shows a real photo of 2 of these storage racks that are allocated per 1K GPU pod. And at the top of the picture, located in green, you see the storage IB switches, the 40 total per pod. And on the bottom in red are the 10 AI400X appliances. These AI400X appliances are all NVMe based. In total, they have a usable capacity of 2.4 petabytes and are capable of very high performance. So these 10 units together are capable of 500 gigabytes per second read and 350 gigabytes per second write. And this 2-rack template is duplicated throughout the 4 different pods in the Selene design, implying that we have a total of 40 appliances. And the capacity and performance figures scale linearly as you duplicate this building block, leading for the full Selene design to have up to 10 petabytes of usable capacity, 2 terabytes per second of read bandwidth, and 1.4 terabytes per second of write bandwidth, which puts us squarely in that range that Julie mentioned earlier of that 1 terabyte per second bandwidth requirement. Next slide, please. All right, so let's take a step deeper into our configuration and what it looks like, specifically with respect to the Lustre design. So we run DDN's Exascaler file system, which is based on Lustre 2.12 at the current moment. Each of these AI400X appliances is configured with 4 VMs, and these 4 VMs in total present a total of 1 MDT and 8 OSTs, meaning we have 20 total MDTs and 160 OSTs in our 20-unit production configuration. We rely heavily on the Lustre PFL to facilitate the striping of our files. We've kind of broken them into what I'll call small, medium, and large files, which in practice is shown to work well for the variety of use cases that we see our users run. And as we alluded to earlier, we're very heavily multi-rail. So all of the client nodes have 2 HDR200 interfaces. The server VMs all have two HDR100 ports as well. And I add some details here for your reference in terms of the configuration that we use on the servers. Next slide, please. So in order to understand how our storage and a lot of the other systems work in Selene, we spent a lot of effort on our monitoring capabilities. So temperatures, clocks, power, capacity, performance, all the way from the individual node to the data center level. And a lot of the charts that I'll show in the subsequent slides are either pulled directly from these views or derived from the data that we get from them. And the picture we have on this slide here is our main dashboard for the file system. So when we log in and look to see what's going on in the cluster, this is the view that we get. Next slide, please. All right. So we've talked briefly about the details of the storage design. And so now let's move on to see how it works in practice. Starting first with some synthetic benchmarks to prove the capabilities, and then we'll move on to real workloads. So this slide is showing some synthetic benchmarks using IOR for a pod's worth of AI400X appliances, so 10 in total. And the chart on the right is showing us running IOR for increasing powers up to number of clients. And there's a couple of takeaways that I want to point your attention to here. At the single client level, our performance for both reads and writes exceeds about 45 gigabytes per second, which gives us a strong indication that we're able to saturate the two HDR200 interfaces per client. And similarly, as you scale the number of compute nodes, we see that we're able to reach that peak value both for the 500 gigabytes per second read and 350 gigabytes per second write, starting at about 16 clients. And we maintain that same performance as we scale the number of clients. Next slide, please. And as I mentioned before, the production configuration for Selene is composed of 20 appliances. So using the same workload that we had in the previous slide, we run that same one on 64 clients against the production 20 units. And we see here that we're able to actually achieve that 1 terabyte per second of read bandwidth and 700 gigabytes per second of write bandwidth. The chart that I have here is actually pulled from that monitoring dashboard that I showed earlier. And this was a very cool achievement to see, even as a synthetic benchmark, as it shows, as we had that 1 terabyte per second design goal through the development of Selene, that we were able to carry that through and see it for real. Next slide. All right, so at this point, you might be thinking, hey, that's cool. You can run IOR really fast, but who really cares, right? What does that actually mean in terms of your applications? And it's a great question. So let's dive a bit into that. So as a brief aside, I'll just mention for those of you who may not be familiar with the deep learning paradigm in terms of what these applications look like, they're very commonly following this type of pattern, where you read a data set, you perform computation on different ranks and all reduce the results between them, and then you repeat. So you read the same data, do more computation, and all reduce, etc. At some point, you might checkpoint, meaning you save the state of the model training to the file system for later use, and then you continue on with reading and computing. So to try and describe the performance of deep learning training on Selene and in our infrastructure, we take two workloads from the MLPerf training benchmark. In this case, we're choosing BERT, which is a natural language processing model, and ResNet 50, which is a image classification model. And for these benchmarks, in order to get kind of the most tuned results, we copy these data sets locally on the local storage, the RAID of these DGXA100 nodes. But in practice, in a real production environment, that's not really a sustainable practice. Not only is it a large overhead for administrators to copy and manage these data sets, but you run into capacity limitations on the actual size of the local storage. And in the case of Selene, most of our data sets are actually on the shared parallel file system only. So to compare what the kind of performance we get between having data sets stored on the local node as opposed to the file system, we run training for BERT with 128 nodes and ResNet 50 using 96 nodes, with the data set stored either in the local storage on the node or on the shared parallel file system. And in both cases, our Lustre file system does very well, providing a time to train within 7% and 3% of the best case training performance for BERT 128 nodes and ResNet 50 96 nodes, respectively. Next slide, please. Another common workload that we see on Selene is Megatron-LM. So Megatron-LM is an open source set of tools developed by NVIDIA's Applied Deep Learning Research team for their ongoing work of training large-scale language models. So it provides the capability to train large, highly capable models like GPT-2, GPT-3, and others, and scale them from 1 billion parameters up to 1 trillion parameters in size. And these are the type of big iron AI applications that a machine like Selene makes possible.
And as we go, if I may, if you remember the first slide, we are on the deep end of the right-hand side here. And so if you hear about, the workloads and the articles on OpenAI, this is the kind of model they run. And just for everybody, it's considered that it's not worth training that workload if you don't have at least 1,000 GPUs. So that's the kind of big, giant limitations of AI right now, where infrastructure becomes the limiter. Sorry, go ahead, Prethvi.
Sure, no, it's a great point. This is kind of really pushing the boundaries of the state of the art of AI and kind of where the direction is heading. With respect to Megatron-LM, it poses a few unique challenges for storage. Because of the size of these models, the amount of data you have to save to capture the state of these models is therefore larger, which means you have more data that you're reading and writing to the file system. Secondly, because of the way that the computation is laid out amongst different ranks, you have multiple ranks which are actually reading and writing checkpoints when you start or checkpoint training. And finally, the ADLR researchers are regular users on the cluster. They wait in the queue. They are subject to job time constraints, which are smaller than the actual full time to train they would need for their models. So they are, reading and writing these checkpoints at the beginning and end of their jobs all the time. And so these 3 points combined make these type of training workloads very challenging for storage infrastructures. Every minute that you're having hundreds of nodes stalled waiting for I/O is wasted cycles, right? And less productivity for our users.
Maybe we should admit to people that our wall time is much less than 12 hours.
Yes.
So we are very stringent on the time limit for job.
Definitely. And so to try and characterize some of the performance demands from these type of models, I'll use GPT-3 13 billion as an example model training on 128 client nodes. Next slide. So let's take a look at the monitoring and see what it shows us for this type of workload. So on the left here, I have, again, the aggregated file system view. And on the right, we have the per node InfiniBand traffic for the storage interfaces. So in aggregate, we see that the initialization of this training on 128 clients reaches a peak of 250 gigabytes per second from the file system. And per node, we look at about 4 gigabytes per second of bandwidth requirement. Next slide. And for the checkpointing side, we see again a per node view of the storage InfiniBand traffic during checkpointing. And here, this single node is writing out about 3.5 gigabytes per second. And in aggregate, we see about 7 gigabytes per second being written. Next slide. And so it's important to keep in mind that GPT-3 13 billion, which I've used for the previous slides, while the storage demands of that model are fairly high, it's still pretty far away from the synthetic benchmarks that we talked about in the previous slides. It's important to keep in mind that GPT-3 13 billion is by Megatron standards a very relatively small model. And the ADLR team experiments with much larger language models and at larger scales in normal production on Selene. And the graph that I have here is an example of the telemetry for the file system during one of these larger scale, larger model variant runs. And during normal production conditions, you can see that that application is actually able to read the full 1 terabyte per second of bandwidth capacity that we have in the file system. And so, you know, again, this looks very similar to some of the previous slides, previous diagrams we've seen, but this is a real application now, right?
And just because it's very small, one of the reasons we do that here, you see it was 2153 and here it was 2155. I think what we're showing here is being able to read in less than 2 minutes saves us a lot of GPU power, because while the reads is happening, those GPUs are waiting, right? And or at least even if they start computing, some of them are going to be waiting. And I think that's for us, that was the big gain here. We didn't want to have that whole infrastructure stalling, waiting for data to come through.
Absolutely. And it you know, carries through that design goal that we had from the beginning. Next slide. Okay, so now let me transition quickly to talk a little bit about ongoing work that we have for leveraging new Lustre features for gaining additional performance for our workloads. As we've discussed before, the kind of DL paradigm, it requires a lot of reading data sets over and over again. Manually copying the data sets to the local RAID on these nodes is painful. And you know, we would like to get out of that business if at all possible.
And one thing we didn't say, we say it's a painful process for admin. I think we forgot to mention that it's even more painful for users, right? Yes. We had some users that you know, they were very positively trying, and this is not the kind of data set you transfer with our sync.
Exactly.
and that's really what we wanted to avoid.
Yeah, and you know, that to that point, right, that leads to a lot even more wasted compute cycles, right, when you're waiting for more IO. So in our idea, we'd be able to have utilize a feature like Lustre PCC to be able to have data sets cached locally on the compute nodes through Lustre, kind of transparently to the users. And so we put all of our data sets on the file system read-only. And the idea is that these data sets would be cached the first time that they were read on a client node. And so you would pay the penalty for that cold read the first time, and then subsequent reads would come directly from the cache. Next slide. And so to try and see what this might look like in practice for our users, we decided to do some experiments with ResNet 50 on a single client to see what the behavior looks like with and without PCC. So quick background on the data set for this workload. It's just a few files, about 150 gigs total size. And our test methodology is as follows. We drop the caches on our client node. We train ResNet 50 for 1 epoch, which means that we read the full data set. We drop the caches again, and then retrain and reread the same full data set again. And so the idea here is we would do this for 2 versions of the data set. One as a baseline, which is not eligible for any PCC caching, and one version which is, which would hopefully show us the benefit of using the PCC. So this chart right here is an overlay of a couple of different metrics. So in the same chart, we have the InfiniBand storage interfaces traffic that is coming from the file system. We have the RAID read and write performance, as well as GPU utilization to show where training is actually occurring. So in this case, we're showing the PCC off, the baseline configuration. So we start by dropping the caches in step 1. Step 2, we start to train. You see the GPU utilization spike. And at the same time, you see InfiniBand traffic from the red and the orange lines. And this goes throughout the first epoch as we read the data set from the file system. We drop the caches again, and then we repeat. And because we've dropped the caches and there's no PCC involved, we find that we are rereading the data set from the file system. So this is our baseline, kind of the current state, if you will. Next slide. And so now we're gonna turn PCC on, kind of like RTX on, right? And so we'll see what the behavior looks like in this case. So again, we start by dropping the caches, and we start to train ResNet 50. And in this case, we see some slightly different behavior. So we see both InfiniBand traffic coming from the file system as we're reading the data set. And secondly, we see a write data going to the RAID of the compute node in purple. So this is that purple line is representing the asynchronous copying of the data set to PCC, while during training, we're reading that data set from the file system. Then after we drop the caches again and repeat training, we see that instead of having to go back to the file system, we're actually able to just read directly from PCC. No need to go back to the file system and use the extra bandwidth. So this was a pretty cool result that shows that you could utilize PCC for deep learning workloads and improve data set access. So now let's try and scale our workload up a bit. So we're using the same workload, but now we'll scale it up from 1 client to 96 clients. And here we will do a full training, which is much faster on a larger number of nodes, and compare the performance relatively for time to train between the baseline RAID, Lustre without PCC, and Lustre with PCC. And some of our early results that we're showing here on the right indicate that for a configuration with Lustre PCC, that there is a performance improvement of about 3%. Some of you might be wondering, why are you so excited by 3%? That doesn't really sound like, very compelling. But in the world of DL benchmarking, right, every % of performance is very important. Yeah. And
for us, that might be the criterion we need for users to accept to use a shared file system.
Exactly.
It's that stringent.
Exactly. So the closer we can drive the Lustre PCC line to the RAID line, right, is a big win for us, right? And that would give us the ability to get out of that local data set business. All right, so I'll go ahead and turn it back over to Julie for the conclusion and wrap up.
Okay, thanks, Prethvi. So mission accomplished. We've shown you 1 terabyte per second. As Prethvi said, for us, performance was one thing, and the community we work with was not necessarily, parallel file system aware. And being able to see that every day in production was a real achievement. A lot of people say, yeah, you have the ID, it's an HPC file system. There was some articles, like I think 3 years ago, that was like, wow, parallel file system are not good for AI. I actually disagree. They can be pretty good for AI. And I think that's what we wanted to show, and we were very happy to see that can work. The solution we have, we're using DDN Exascaler. It's very convenient for us, but it can be implemented on any Lustre setup. And here, that's usually where I apologize to Andreas and James and everybody when we do, and especially to DDN support, because sometimes we do, I'm going to call that exotic experimental things with the Lustre tree, and we have a little bit of, you guys did what? I was like, yeah, we wanted to try. So, that's why I thank them for, putting us with our random experimenting behavior. But basically, if you already have a Lustre setup and you have performance requirement, it's just mostly the strategy, and we were very happy to be able to show that the strategy actually could work. It's very flexible and simple. You heard Prethvi said we really want to get out of that dataset copy business. So basically for us, it's everything should be easy for users, and the users that we serve are not file system people. We have users that was like, what's the matter? And I'm pretty sure you can relate to that. What's the matter with having 15 million 4K files in a single folder on Lustre? I'm like, okay, let's talk about this. But basically, we managed to have that, and we managed to find a solution whereby both educating our users to dataset file size, tuning a little bit, and making sure we use cache efficiently, it's very convenient for all. It's very reliable. So I've, for personal reasons, I've been close to the Lustre community for a while. And, I would say that 15 years ago, when you say, oh, I'm going to use Lustre, people were like, ooh, really? No, for us, it's been very reliable. And even if we, play experimentally with it, everybody that we dealt with, we're very happy about it. Both the file system is reliable, but also the multi-rail aspect. We know it's relatively recent. That's something we really rely on. So there was a little bit of anxiety in there, but it's that the performance is just amazing, and that's pretty cool. We're very excited about the newer features. PCC hot nods and something. It's really something we would like to see. It's my opportunity to thank the people that managed to make it happen for us. And yeah, I know it as Prethvi said, we fight for 3% performance, but it's 3% performance right now. And I think we really want to see that through so that eventually people can reliably say, yes, we use Lustre for AI, and that's great. And that's about it. A couple links here, and we'll be happy to take questions. Thanks.
Okay, thank you very much. Thank you very much, Julie and Prethvi, for this very impressive presentation, I would say. Congratulations on the performance you got. And we're running a little bit behind the schedule, but we do want to take a look at the questions because apparently people are very interested in your excellent presentation. Okay, let's take a look at the questions. First question is, any information on the IOPS on the DDN AI 400X per appliance?
That's a very good question. It's not one we have looked at extensively. So I must admit, unfortunately, that's not a criterion we've been looking at. I mean, if James still here, maybe he can chime in. We had that in an early benchmark. We don't run object. We don't run data sets that are well suited for IOPS heavy. So it's not a criterion we've been looking at. But if folks are interested, they can reach out to us on the side and we can get them the data.
Okay, thank you. And the next question is about the GPU Direct. I think there are some answers already in the chat. Do you have anything to add on?
So on Selene, the way we design is to have storage very separate from the compute by design. Because for most of DL, the IO pipeline still goes through the CPU. And the GPUs are so heavily used that we don't want to mix and match over there. So here we've shown you only a subset of the applications that are very GPU heavy, and they are so GPU heavy that we don't want to do the storage on the GPU. So we have GPU Direct all the way through the compute. The compute here, we could enable, and we've done that in the previous cluster we had, and we could enable at any point adding storage on that compute platform. On Selene, we don't have it because we really need the GPU performance above all. And some of you might have seen Selene presentations. Usually we talk about compute. It also took us sometimes to look into storage because we spent the most of the effort making sure compute's right. So you could do it. We don't run it in regular production.
Okay, thank you. We have another question asked about the issues with co-locating MDTs and OSTs on the same exact VMs. So especially when there are heavy loads. Do you have any issues on that?
Prethvi, you want to come in? It's from our IOR experiment in the past.
Yeah. No, I think it's a good question. I think in general for the workloads that we see, it hasn't been any particular issue that we've run across. Certainly, when you get into applications that are more metadata intensive, workloads like Julie mentioned that are lots of small little files that are being read, that can be a bit of a challenge. But I think in general, no issues that we've come across in that respect.
In a way, we're lucky too, because our users are our colleagues. So we have the opportunity, or it might be easier to work together to have overall education on how we can get performance together, right? While we've been playing experiments with containers and different clients, etc., for IO 500 experiments, for example, in that context, we put each other in the easy case, and we basically evangelize the easy case to users. So we don't see any more users that have a lot of, metadata access. I know in French we call that gardening in the file system. I don't even know what it's called in English, but we managed to work a relationship with our users so that they understand that we didn't tune for that.